So we're doing gliding flight. Thrust is 0. So let's draw our airplane again. So here's the horizon. And I'm going to draw the airplane going the other direction so that you can see that it doesn't really matter whether we draw it going to the right or the left. The angles and everything are still the same. So there's the airplane. There's essentially the chord line through the wing, like we drew before. The velocity of the airplane is in this direction. So this is still the angle of attack, the angle between the velocity vector or the relative wind and that chord line is the angle of attack. And then this is the flight path angle, theta. And we still have lift perpendicular to the velocity. And we have weight down. And we still have drag parallel to the velocity. Like that. And we still need to break the weight into components perpendicular and parallel so that we can look at the forces perpendicular and parallel to V infinity. So this angle is theta, because that's how much it's tilted up. And so this is W cosine theta. This is W sine theta. Let's move the W over to the big vector over here. And notice the thrust is missing because the thrust is 0. So if we look at the sum of the forces parallel to the velocity, we have no thrust. So we could put that in there and say thrust is 0. Minus the drag, drag's backward. And then we have this component of the weight here. And that's equal to the mass times the acceleration. So that's the forces parallel. And then here's the perpendicular forces. We've got lift up minus W cosine theta, so that's the component down that way. And that's equal to the centripetal acceleration required if we're curving. But we're doing straight line flight here, so we're going to say this is 0 for a straight glide. So we're not doing a pull-up kind of a thing. We're just gliding straight. And whether we'll look at the figure again in a minute, but let's look at this equation. And we can immediately tell that we can't get a case where the velocity change is 0. Because here we got a negative number and a negative number. And so that means that dv by dt is negative, so the velocity is going to be decreasing. Well, how did we solve that before? When the thrust was non-zero, then the thrust could be some positive number that was equal to these components here, and we could get 0, we could get static equilibrium. So the problem is thrust is turned off in that equation, And if you just look at the picture here, you can see thrust acting backward, weight acting backward. I'm sorry, drag acting backward, weight acting backward, and there's nothing to balance it out. So pretty clearly, if we try to go up with the thrust off, we're going to keep slowing down. Now you can do that, it just means you're going to lose airspeed, eventually stall, and fall out of the sky. So what that means is if we look at this equation, if we want this equation to balance out to give us 0 acceleration, if we want to get that, we need to have drag, move the drag over to the other side. We need this thing. We can't make weight negative, so we need this thing to be negative. So we can have, if this will work, if theta is negative. Right, the equation says that works. The picture also says it works because if we tilt theta down negative, then the weight vector is going to be acting that direction, and the weight vector will balance out the drag, and everything's good. So we could go from this equation and just realize that theta needs to be negative. The book draws a picture of this diving down for a gliding flight, so I want to redraw that. So that you can see how the components work on that picture. But the equation says, yeah, this is going to work. So let's tilt the airplane down. So we still have the horizon like this. And the velocity vector is going down like that. So now this is the pitch angle, but we've defined theta as positive up. So I'm going to call this theta hat. And in fact, that's going to be equal to the negative of the theta that's defined positive up. So now the airplane's pitched down. The lift is this way. The drag is this way. Here's the weight, and we've got components of the weight, perpendicular and parallel. And you can see that we've got a weight component opposing the drag, just like this equation, except now theta hat is the negative of theta, so that takes care of everything. And from the picture, it's going to work. Yeah.
What's that line between velocity and the horizon line that your angle is at?
Which this is the chord line. Yeah. Where does it go here? Yeah, and this is alpha. Because alpha is always the angle between the velocity vector and the chord line. Yeah, good question. So in the book, he does everything in terms of this picture and theta hat. So the equations that go with this . And notice that the cosine doesn't flip sine because cosine of negative or positive is the same thing. So these are the equations for gliding flight. And we're going to use these. for our analysis. But I want you to be able to draw this picture, because if you drew this picture and you pointed to it to somebody that didn't know dynamics or anything like that, you could say, hey, look, this force balances out the drag, and this force is balanced by the lift, and everybody go, oh yeah, that makes sense. Okay, now I have to do a caveat. In the book, he does not do this. He draws this picture and calls this angle theta, not negative theta or theta hat. He really ought to fix that, because it's confusing, because you look a couple pages earlier and he draws it pitched up, and that's theta, and then in this section, it's theta pitched down, and there's a contradiction there. So what I recommend you do is go into your text, and in the section on gliding flight, you put a hat over theta in the picture and in the equations, just so that it's not confusing. So this is static equilibrium in the parallel direction. This is static equilibrium in the perpendicular direction. And again, we're not curving, so we don't have the centripetal acceleration. So questions about this? Again, it's just a free body diagram. We do the forces in two different directions, and that's what we get. And either from the picture or the equations, you can see that you have to have theta as a negative angle in order to balance out the drag. So the key features of drawing this picture is you draw the airplane, and you draw the chord line, and you draw the velocity vector in the direction that it's going, and then you write your angles in. The alpha is always the angle between the chord and the velocity, and theta is always the angle between the velocity and the horizon, no matter what you're doing. So if for some weird reason you're on your airplane and you're climbing straight up, here's the horizon, this is theta. And the angle of attack here would be 0, because I've drawn the velocity directly along the chord line. If the chord line's tilted a little bit from the velocity vector, then the angle of attack is there. Okay, so we're going to start with those equations. All right, so we're going to divide the perpendicular equation by the parallel equation. So that's easy to do. It says lift over drag equals W cosine so the weight cancels out. So it doesn't matter in our equations now what the airplane weighs. And let's flip this over to this side. So we get sine over cosine, because that's nice, because we usually deal with tangent. All right, so I just did some algebra. And if we use our definitions for lift coefficient, I can divide and multiply by Q infinity S. Right, those cancel out. And I can put this in terms of lift coefficient and drag coefficient if I want to. But in either case, either CL over CD or L over D, if I want the smallest dive angle or gliding angle, I need the biggest L over D, or CL over CD. So that's the lift to drag ratio. And remember, we've talked about this a couple times, is that's the efficiency of the airplane, because lift is what we want, drag is the side effect of producing lift. So if we get the most lift for the least amount of side effects, then we get the best glide angle. So if you were going to design your glider to fly at the shallowest angle, you would just maximize CL over CD. And let me draw a picture of the geometry of the airplane flying. And we'll find out that this is also the same condition for going the farthest. So if you're at a certain location on the Earth and you want to glide as far as you can, you fly at this condition.
Isn't that equivalent to the CD over CL? Like, you just take your
Oh, yeah, but I write it like this because we've already talked about CL over CD max as being the efficiency. Yeah, of course, you can flip the CD up to the top. So if we draw a picture of the airplane in the air and then gliding down to hit the ground, here's what we get. So here's our airplane at an altitude h. And it's gliding along this angle, which is theta hat. And then here's the ground, the horizon. This is angle theta hat, of course, because it's the opposite angle like that. And then this distance here, where it hits the ground, is what we call the range. That's how far downrange it can go. So if you're at altitude h, you can fly at that angle. It's just a triangle. And so you're going to hit the ground after a distance r. And we see from the geometry of the triangle here that the tangent of theta is h over r. Or if we're trying to optimize the range, build the r over here. If we fly at this smallest theta angle, we're going to go the farthest because we get the tangent smallest. And that makes sense as well, right? If you make this angle as small as possible, you're going to be able to go farther. It's just geometry. So both of the conditions, this is CL over CD max again. So to go the farthest, we do that. So how about your challenge or your requirements is to stay in the air the longest? And that's a little different than this. You would think, well, that's the solution is right here. But this doesn't say anything about how fast the airplane reaches the ground. Because we may fly at a really shallow angle, but we're going fast. And so even though we go farther, we hit the ground sooner. So the next thing I want to talk about is time aloft, which is what you're going to be doing. But I want you to understand this as well. This is important. Because if you're in a powered airplane, and the engine quits, and you need to know, well, how far can you go to get to a runway? This is the equation, and this is the condition you want to fly at. You want to fly at a velocity that gives you CL over CD max. The reason that I did time aloft for the challenge is that in X-plane, figuring out where you hit the ground and then measuring back to where you started would be hard, and with time aloft, we can just do the stopwatch. And it also makes it a little more challenging because you're going to have to calculate time aloft and optimize that. Although I'll show you it's not that big a deal either. And again, all this sounds like an academic exercise unless you want to know how far you can glide and whether you can make it to a runway or not. So time aloft for a glider. And we'll also talk about this for a powered airplane, but that's more with how much fuel you have on board and how long you can fly on that amount of fuel. In this case, the fuel is your altitude. That's your energy is coming from your altitude and you're hitting the ground. So let's draw a picture of our airplane again at an altitude H and a range R. And there's the flight path and angle theta. So our airplane's following that path there. But instead of talking about the geometry of position, we want to talk about the vector triangle of the velocity, right? This is the flight path. Let's draw it on the flight path. So this is the velocity vector here. V, so that's how fast the airplane's going along that angle theta. And we can take the velocity vector and divide it up into ground speed, V sub g, and an altitude rate. And I'm making that minus h dot because we're going down. All right, so h is decreasing, so h dot is negative. And from this triangle, h dot is going to be v sine theta hat. So if we look at that, now what you're going to be doing is you want to minimize h dot. You want to minimize your sink rate, which is v sine theta. So you're not minimizing just theta, you're minimizing the combination of the velocity and the angle. And you can calculate the time aloft. What we're going to do is we're going to say we're at an altitude h, and we go down and hit the ground at that velocity. So it's just integrating velocity and time. So minus h dot is minus dh by dt. So if we want to calculate the time, put the dt over here, and really this is velocity time diagram. We can integrate this. This is dt and dh. So we integrate this from time 0 at altitude h to hitting the ground, which is a 0 altitude, and that is our time aloft. So at this position up here, we're at h and we're at t equals 0. And then down here, we're at h equals 0 and t equals t aloft. And all we do is add up all of the h dots. Or you can even think of it as simpler as this is distance per time. So we're just figuring out what time it takes to go that certain distance down. So integrating this is real easy. And the sign flips here because the limits are backwards. So that's a real easy calculation. Is you know what altitude you're at, and then you vary your airspeed and figure out your angle here, and then you optimize that. So in fact, we're going to do that. We're going to plot time aloft versus airspeed, because that's going to give you your optimal target airspeed you want to fly to stay in the air the longest. And we'll also plot h dot versus velocity, because h dot is a function of velocity as well. So in reality, it comes down to minimizing h dot, your sink rate. And if you minimize that, you stay in the air the longest. So here's how we're going to do the plot. We're going to use this formula for h dot, and then we're going to integrate it to give us the time aloft. So we're going to plot h dot versus velocity. So what is h dot? It's that formula there. And how do we get the angle? We showed that. The angle comes from CL and CD, and we know formulas for CL and CD. It's weight divided by Q infinity S. Oh, by the way, we're doing this for that Cessna piston engine jet. So we're pulling the data from the book for that. There's the weight. We're going to calculate Q infinity, and the area is 174. So let me list the data up here. Weight equals 2950. This is from the book that we got before. Area is 174. The efficiency factor is 0.8. Aspect ratio for this thing is 7.37. And why do we need that? Because we need that data to get the drag. So then CD is the CD0 plus CL squared over pi E hat AR. So we should add that to the data here. Our CD0 that we were given was 0.025. And that's everything we need. So first thing we're going to do this backward. We're plotting h dot versus velocity. So we plug in a velocity here, calculate Q infinity. Q infinity goes in here to give CL. CL goes in here to give CD. And then we get CL over CD, and we calculate our angle theta, which then goes into here, and we plot. So again, I listed all the equations that we needed to calculate this, and then we look at, well, what order do we need to do this in? So let's do this in a spreadsheet. Is everybody following through? Do I need to explain how we're doing this? Again, we're plotting this versus velocity. So velocity, that's going to be an independent variable. We need to calculate theta. Theta comes from this. Well, we need CL over CD. So here's CL, here's CD. To get those, we need Q infinity, which depends on velocity, the independent variable. What is what?
I didn't hear what you said at the end.
Velocity is the independent variable for the plot, yeah. So we're going to have a column for velocity that's going to go into this equation in the next column. That's going to go into this equation for the next column, which is then going to go into this equation for the next column, which is going to go into this equation for the next column, which is going to go into this equation. So let's walk through that. And that's exactly how you would do it if you were hand calculating this, right? If I said, in fact, we're going to do this for 60 feet per second, plot H dot. Yeah. I'm sorry. Oh, this is all English. Yeah, I should put that up there because a number without units is useless, right? Aspect ratio, CD0, that's unitless. Aspect ratio is unitless. And E hat. Good question. My physics friends would be groaning at this point. So here's our Excel spreadsheet, and we're going to put in velocity in feet per second here. And we're going to put in dynamic pressure. By the way, we're doing this at sea level. I didn't specify that, so make sure you write that in your notes because we're going to pull the density from sea level. So there's going to be our column for the dynamic pressure. And then we need a column for CL. And we need a column for CD. And then we need to calculate 1 over CL over CD. And then we're going to invert tangent that to get theta. And then we're going to stuff theta and the velocity into the formula for H dot. And then we're going to do the time aloft from 1,000 feet. So we're going to use the formula for time aloft to get that. So I started at 60 feet per second and varied it by 20 feet per second. So if I type both of those, it knows what the increment is, and I can drag this down. I think 320 is good enough here. So the dynamic pressure, 1/2 rho, the density of rho is at sea level is 0.002769. And then we got to multiply it by V squared. So if you're taking notes, there's the formula that I used for Q infinity. Is that big enough to see? Let's see if maybe I can, yeah, this works. Because there we go. So 1/2 rho V squared. We're good there. And let's double check my number. There seems something 27. Would somebody do a hand calculation and check this dynamic pressure? They look right. I know what the problem is. What's the density? Look up the density at sea level. I've got that wrong, don't I? It's 23769, right? Like that? Yeah, so check my hand calculations there, and I need to, there's a typo in my notes. Does that, anybody have a pen? Or no, I've got a pen here, never mind. And I need to drag that down again to change that formula. So everybody do a hand calculation on this to make sure that we've got the right number there. And when you do homework, I will have you do that. I'll say, make a spreadsheet to do this, show me hand calculations for one of the rows of velocity of, say, 100 or something like that. Okay, so the next column is CL, which is equal to the weight, which is 2950, divided by dynamic pressure times the wing area, which was 174. Somebody check that calculation. In fact, everybody check that calculation. And the number that I have in there is 3.9625. Is that correct? So we validated that. We're good? Okay, and then this is going to be the profile drag plus CL squared. So I'm going to grab this column, square it, divide by pi, and then E hat was 0.8, and the aspect ratio was 7.37. So go ahead and run that calculation on your calculator. Let me punch that up there. We should get 0.873. Is that good? Okay, everybody take a minute and do that. So can I move on? Are you guys all caught up? I want to make sure everybody's doing this. Everybody else good? And then this is easy to calculate. 1 divided by CL divided by CD. So somebody check that calculation. And then theta is going to be the inverse tangent. And I've forgotten the function for that. Is it? I think it's arctan. Let's see. Nope. Atan. There we go. And then I forgot to type in the rest of it. Atan of this. And so this is in radians, of course, because that's what Excel does. That's an easy calculation. Just plug that into your calculator. And then H dot is the velocity. And I want this to be negative. I need to put a negative sign there. minus the velocity times the sine of theta. So that says we're going downward at 12.9 feet per second. Somebody check that. Good? Everybody getting that? So the time aloft is going to be the altitude divided by that number. And I lost my minus sign on the board. No, I didn't. We're good. There should be a hat over these, though. All right, so the time aloft is equal to, we said we were doing this from 1,000 feet. Oh, I didn't mess up. And I still have a sign. Where did I mess up my sign? That flips it there. Oh, that's because this is, H dot is negative and V sine theta hat is positive. So I need to flip the sign on this. Okay, so let's drag this down so that we know the value at each different velocity. And then let's plot time aloft versus velocity. So we look at that and we see, well, here's maximum time aloft right here. And we look down here and we can see the velocity that we would want to fly at to stay in the air the longest. Yeah. I'm going to come over here so I can hear you.
I just missed it. How did you get the graph on Excel?
Oh, it's insert XY chart. I'll do that again. So let's delete this chart. So I clicked on this and highlighted that column, and then I do a control, click on the column that I want to plot. So this is going to be the x-axis and this is going to be the y. So you select this, hit control, hit that column. So far so good. So now it's going to plot these two columns, and then I do insert. And then over here is this scatter XY. Don't want to do this because it plots versus the 1, 2, 3, 4, 5. So you're doing this called the scatter. And then I picked that it fits a line rather than putting the individual points. Let's do this when it shows the points and a curve fit. Did that help? Okay. But we didn't need the plot to tell us the maximum, because we could have looked down this chart, down this column here, and picked this and this airspeed as being the maximum time aloft. It's also the minimum H dot. Makes sense. We talked about that. The minimum sink rate is going to give you the maximum time aloft. But notice that this is not the minimum theta. The minimum theta is down here. And that's because they're two different optimizations. And it's because in the H dot, you have the V times the sine of theta. So minimizing theta does not necessarily give you the minimum time aloft. And notice that the minimum theta occurs at a higher airspeed than the time aloft does. And that's what makes the difference. Here you're flying slower. You're flying at a slightly steeper angle, but you're flying slower. And so you still stay in the air longer before you hit the ground. So this is the kind of plot that you will want to do for your glider when you're designing it. And you could plot, I think I asked you to plot time aloft, but where you optimize it is in H dot. Yeah.
How do you choose your airfoil in relation to that data?
That's the design problem. If you notice, I've limited you to 2 different airfoils. So you'll want to do a trade-off study of not just your airfoil, but your aspect ratio of your wing as well. And we've seen that in the drag, the aspect ratio affects the drag, right? So it's not, oh, well, I just do some calculations and I come up with the best answer. You'll want to try different things, because if you go with a high aspect ratio wing, you minimize your induced drag, but you might increase your other drag and because of the lift. And so you'll be trying different things and doing this spreadsheet for several different aircraft designs to pick your best design. All right, we're a couple minutes over, so we're done, but that's gliding flight. Next time, and there's a chapter in your book on this, so make sure you look at that. And then next time we'll go back to our thrust required for level flight and look at thrust available and power required and power available as well.